Evening, everyone. Welcome back to today's live session for week 9. So, as we were talking about cross-coupling reactions, we have covered 4 to 5 cross-coupling in the last session, and we ended up our topic session with still coupling, and we will be continuing with that and introducing hydrocyanation and some other cross-coupling reactions, heterocoupling reactions as well. So before moving ahead, if there is any question or any doubt from previous sessions, please let me know. And at the end of this session, we will be discussing the problem sessions, problems, whatever has been given in the assignment. So I'll wait for a few more minutes for others to join. And please let me know if there is any query. Due to the network constraints, I cannot keep my video on for a very long time. So please bear with it. If at all you need my video to be on, please let me know in the comment section. Thank you. So let's start our session. So we have ended the session, as I mentioned, we ended our session with still reaction. So let's introduce it one more time. So what is basically the still reaction? So this is nothing but your combination of generally, this is when you are introducing the carbonyl group. In the last session, what we saw that general reaction for still is when you are treating one uh, group having an halide. This R1 can be alkyl, aryl, anything. And on the other side, we have a thin orbital. And in presence of our palladium catalyst, where we can define your X can be bromide, iodide, OS2CF3. So what is going to happen? This is going to couple with this R2 group, giving you R1, R2, and then we'll be taking your halide. So SN, R3, 3. So this is your general still reaction, which we have discussed in details in our last session. If in presence of carbon monoxide, that is CO2, we can get ketone formation. It means now if we have R1X, same reagents, 3, in presence of palladium metals, we are also introducing carbon monoxide. So it will give you a product of that insertion of CO will happen, and you will end up getting a ketone instead of a CC coupling directly. So this is the reaction that we have started. What we are going to talk about today is basically how the ketone synthesis can be understood and performed. We have what we can take over here. We can have acid chlorides. One method was to introduce carbon monoxide. Another method is to introduce acid chloride and treat it with tin organelles. What are the conditions? The acid chlorides, they can be sterically bulky, or what we say is hinder. So that means that RCOCl that you're going to take, that can be having the steric hindrance, which is not going to affect the reactivity. And also you can consider alpha beta unsaturated acid chlorides as well. So steric hindrance or alpha beta unsaturation is not a problem. It has a tolerance with that. What it has been found that interestingly, the R2 SNMe3, here we are replacing the R3 as methyl group. It does not found in reacting with the ketone form. So generally it shows a reaction. So your ketone, the product that has been formed, is not going to get reacted with your thin organelle, and you end up having your product with no side products happening. So what we really are saying is we have R1COCl. This is your acid chloride, and we are treating it with trimethyl tin R2, where R2 is the group which is going to get coupled in presence of palladium Ln. This is your catalyst, and this is your tin organelle. So what we are expecting that this part is going to couple with this part, and we will have R1CO R2 plus ClSN full twice. This is the ketone, the second method of making the ketone without introducing the carbon, but starting the reaction with the acid chloride. I hope this is here. If there is any doubt, please let me know. So here we have tried to introduce the acid chloride and inorganic and using of palladium 0 Ln. Ln can be a number of ligands that you can bind with your palladium. Generally, it is L4 or L2. And what we are getting is R1 COs. So that means that there are other possibilities to get your product. So only one such process is not there. You need to be very careful about other processes as well. Okay. Now we can continue with. So there's another topic which is asymmetric still reaction. So here what has happened when we are having a direct coupling of benzyl halides and inorganils. Inversion of the configuration has been observed. This is due to inversion oxidative addition and retention reductive elimination. So as we know, we have already seen the mechanism of still reaction, and here there when we have already seen the mechanism of the still reaction, where we have already talked about that oxidative addition is the first step that is going to happen, and at the last we end up having a reductive elimination. So when we are treating benzyl halides with inorganils, we end up seeing inversion of configuration. This happens because inversion has happened at the oxidative addition state, and whatever the stereochemistry it has taken, that would be retained when it is going to leave. It means reductive elimination step is going to retain the whatever the configuration it has taken. What which means we have HC, and if this H we are going to have with carbon, and here it is deuterium and vinyl bromide. So this is your chiral set. Whenever we are talking about asymmetry, that has to introduce the chirality. The chiral center has to be there. So this is your chiral center because all the four moieties are different. And when you are treating it with methyl 4-SN, which you can also write as methyl SN, and other three methyl are separate. So this is the alpha that is going to it. Now in presence of palladium Ln, what we are expecting is now at this side methyl should come, but it actually undergo the inversion of configuration, and H is at the back of the plate, it's in front of the plate, and pH plus Br Sn Me3. So this is basically the inversion of the configuration has happened. Moving ahead, so this was all about the still reaction. Now we are going to talk about the Sono-Kushida reaction. So this is basically an alternative sequence astrocoupling of copper organelles and the organic electrophiles, which take place under mild conditions. So we have R1X plus HC triple bond C R2. And here we can see that there is R1, which is one group, and there is R2, which is in two. This R1 is going to couple where H is going to be lead in presence of palladium catalyst, copper iodide, in presence of base, triethylamine, and PPC. What we can expect is R1 is coming at this position, and you end up giving amine will take up the proton, making positive H, balancing this reaction by giving an ion which is X minus. Now here X is your bromine iodine, R1 is your aryl group, that can be alkyl group, it can be acyl, and it can be amino acid. Any of these groups can be possible, and R2 is widely variable, which you can use. It can be alkyl, aryl, anything. So this is where Sono-Vishira coupling reaction comes into the picture, where now we are introducing co-catalyst, which is copper iodide. Right? Now moving ahead, what are the possibilities and what are the things that are important for Sono-Vishira reaction? That it involves the transfer of alkyl moiety from copper C R2. So whatever the substrate that you have taken, this is your alkyl group, which reacts with your copper catalyst and gives you copper C triple bond Cr. We will see the full mechanism. These are just the small details. And this to the palladium, it actually transfers this whole group to the palladium, which is known as transmetallation step. So whenever you have one metal center, I'm writing is M1, and it is having a group R1. And another metal you have, which is maybe M2 or something. And now this group gets transferred to this one and forming M1 separately and M2R. This is being known as transmetallation. Let's see one of such reactions. So we can see one example where we are having down groups in the C5H11 chain during the hydroxyl group. And here is a moiety which is having a leaving the light, which is here. And we are treating it with alkyl, which is TMS substituted. Now, the conditions that we are taking here is this is a solvent molecule which is being connected with your palladium catalyst, making a potential of 4 in THF solvent. We are giving a co-catalyst as copper iodide and a base IPB at room temperature. So what we expect over here, that this Cl is going to go out and it is going to get connected with you, because this side is H only, so it will be taken by the 5 and ultimately what you will end up having is this group. And now the new bond has been formed between the and here will be TMS. So this is the new bond that has been formed, that is CC coupling. And this has been given by Magnus in 1990. I hope this is clear. If not, please let me know. So basically, we've understood that this is a co-catalyst which is going to participate in the reaction. and this eventually makes a bond with your, this removes your, in presence of the piperidine, which would take out your H and copper connected with your, you can understand the mechanism in this particular way, that the simplest way is if you have an alkyne and here I'm having a CH3. Now I'm having any nitrogen base is there and it takes up the proton and it creates a charge negative onto your carbon center, which is having triple bond CH3. Now we have, because this would be forming a proteated, that means the charge has to be balanced. That minus and this positive, this goes in coordinate with that one. And here the salt forms as copper, positive C minus, triple bond CCH3. Once this forms, it can easily transfer this group to your palladium group when it comes into a catalytic cycle. So this is the way where we see the role of copper to happen. Moving ahead, the next coupling reaction that we have is hydrocyanation reaction. So far we have seen the coupling reactions made in presence of boron organelles, boronic acids, tin organelles. We saw in presence of copper iodide. Now here, this is basically a coupling reaction, CC coupling reaction. By the addition of HCN. This is your nitride to alkenes. These are the substrate. It can be added to alkynes. It can be added to carbonyl compounds. Therefore, leads to the formation of different types of nitrides, substituting nitrides. So generally, in this particular reaction, we use a nickel catalyst. It is being used for hydrocyanation reaction. So we can see one such example. If I'm taking the 1,3-butadiene, which is a transposition we are taking, there are two ways of making this one. So this is more stable. This is the transform. So taking this as a substrate. Now it is being reacting with nickel L4, where L is your ligand, and HCN. This is your region where you are going to introduce your H as well as CN also. Now what would really happen? The H would go and bind at one side and CN on the other side. So if your CN attacks on this position, this bond would shift here. This would create a charge of this carbon. If I name them, because there are 4 carbons, I'm naming them 1, 2, 3, and 4. So 1 has been taken by Cn, and the double bond has been shifted now to 2, 3 position, and 4 is being having a minus charge, which will attack onto your H positive. So therefore, ultimately you will have double bond Cn, where this side it is connected to the H. Now again, still have a double bond, as we mentioned that the reagents or the substrates for this particular hydrocyanation is alkene alkyne. Firstly, we have hydrocyanated one double bond. Now we have another double bond. So they will be treated with nickel catalyst in presence of HCN. And what we can expect over here, it is again going to form, if at this position now, CN is going to attack, if it attacks onto your so if CN comes and attack onto this position and positive and negative charge is been balanced, and hydrogen, the proton has been taken by the other moiety. First will be formed reaction product Cn and Cn. So if we continue doing this, it actually forms an ion 6, which happens from the adiponitrile from deuterium and HCl in the presence of this particular ligand. So what is the mechanism for this one? Basically, we are starting with nickel L4, which is our catalyst, in combination of HCl. So here what will happen, it will lead to the two ligands, or on the pathway direction, it can gain two ligands. Here ligand, we are talking about a phosphate-based ligand, orthotoluene. Now what it would form, it would undergo an oxidative addition where it would form an H bond with Cn and 2L. Now the reaction starts. Now we are introducing here our alkene, which is our substrate. So this is our first. Here it would try to coordinate with this one. This pi bond interaction would happen with the nickel center having H, Cn, L2. Followed by that, the second step would be, once it is interacting, it will form RCH2CH2, a sigma bond with nickel. And because the hydrogen will be transferring to one position, going this side, and pi bond would shift to your CH2 having a negative charge and then binding with nickel. And nickel would end up having Cn and 2 ligands. Now at this step, this RCH2CH2 can bind with your Cn and leave as your product RCH2CH2 Cn, where the hydrocyanation has happened, and it would release nickel L2. Now at this step, again, when you introduce your HCl, this is your fourth step, it would again form nickel HCl, and the cycle continues. Sorry for the drawing, this is not looking like a circle, but it's actually a complete cycle. What we started with, what active catalyst we are making, how it is participating in the reaction. First insertion is happening, formation is happening, then insertion has happened, then reductive elimination has happened, and at the end we are having an oxidative addition. Or you can consider as first oxidative addition, but that's not a part of your, if you consider this one also, there at the first step, you need to lose 2 ligands, and then HCl, the oxidative addition will happen. So depending upon from which step you are starting, the series of steps would be changed. So understanding it in a better manner. So this particular cycle of hydrocyanation involves the following steps. The first one that it has is coordination of the alkene or alkyne or carbonyl. As you can see here, here the coordination is happening where the pi bond is interacting with your nickel center. Now the second step, it is going to get inserted in that one because it is making a sigma bond. So your second step is insertion. Now again, if you see at the third step, this particular RCH2CH2 moiety and the Cn moiety is undergoing the reductive elimination and forming a product. So your third step is reductive elimination. And the last, we have an introduction of HCN again, which is your oxidative addition. If there is any doubt, please let me know before we move ahead with an example of hydrocyanation.
Ma'am, what is that ligand P O toluene thrice, ma'am?
So you can consider it as orthotoluene you might have seen.
Okay, ma'am.
So basically, generally when we are talking about a phosphine group or phosphine oxides also that matter. So you have this is your benzene, and then when you introduce a CH3 group, that's your toluene. Is that fine? So this is your toluene, and if at the other end you have an oxygen which is binding with your phosphorus. So this at the para position, these methyls can go on the other position as well. Or another way of different phosphines you can try. It is not necessary that you just need to, because the ligand phosphorus is going to coordinate via its lone pairs of electrons. So making a PPH3 or taking some other, if you have substituted chlorine group, which it is making with this one. These are all different types of ligands which stabilizes your nickel system. That's where we use these ligands for this kind of reaction. Is that clear?
Yes, ma'am. Thank you, ma'am.
So now we can move ahead. We can consider one example, which is it's an example of asymmetric hydrocyanation. So whenever we talk about asymmetric, that means it is going to give you some RNS isomer, some chirality has to be there, and where we are trying to form and treat it with HCl. Now here the catalyst is your nickel cord. This is not going to, this is not chiral. For introducing chirality, you're expecting to have some chirality into your center. And the ligand, because cord is going to come out, and here we are adding a phosphinite ligand. This is your ligand, 1,2-diol, and in a solvent medium as toluene, 25 degrees. So depending on different reactions, it can work, and the solubility of your reagents, your solvent and temperature conditions and the ligands would be changed. So what we expect here, we just need to see this is our reagent, this is our attacking position, and this H and CNS needs to get connected with that one. I'll make the product, and here it was H3CO, and this phase it is going to make this bond H is here and CN will be here. This is going to give a H to CH2. This is already CH2. When it will take a H, it will form your, this is already having, when it is not mentioned in this H only. So CH2 will take up the H, making the CH3, which is this group, and other H is already there, and CN would be getting a dimension. This is kind of a chiral center where all your centers, all your groups connected with this carbon is different. So this is a chiral, therefore generated asymmetric system. We have certain, at this point of time, we have covered all the main coupling reactions so far. So Nogashira still like these reactions have been covered. Now, what we have in hand, the next topic is C heteroatom coupling. That means what are the different types of coupling between a carbon and a heteroatom? Heteroatom, we know there can be sulfur, nitrogen, oxygen. So here we can name them. So in general, so they require no very drastic conditions compared to when we do an addition with kenes or alkynes. So first is amination of arenes. That means CN bond formation, hydroamination reaction. Third is hydroboration reaction. And the last one is hydrosilylation reaction. So earlier we saw hydrocyanation, how the hydrogen and cyanide group is attacking, getting added onto the substrate. Similarly, these are the different reactions that we are going to talk about one by one. So let's start with the elimination of arenes. Elimination of arenes. So this also involves a palladium-based catalyst. And here the deductive elimination is the profit. So we can consider if you have any aryl group, it is bound with. So this is the last step of this reaction, which is the reductive elimination. So what it really will do, it will go from plus 2 to 0 and from ARX Rn, where your X can be oxygen, can be sulfur. If that is the case, then your N is 1. Considering the valency of your oxygen and sulfur because they are trivalent. Nitrogen, if it is, then it would be N equals to 2. Let's see the reaction. So this is basically the reductive elimination step that I'm showing. Here, which is the end product, end step of your reaction where your product is going to be formed. Let's look into the mechanism. We are starting with a L2 palladium, which is your catalyst. And here I am introducing aryl group. Here AR can be any substituted benzene group. Now what we expect over here, this is in zero oxidation state. It would undergo an oxidative addition. I'm writing as oxide. So it would form L2 palladium, Ar and Al. Now we are introducing our substrate, which is your heteroatom substrate, the amine group NHCH2, R1 and R2. Now it is the second step where we are expecting it to get inserted in this one. So it will coordinate. One of the ligands would go out, and because we have the two ligands, already the coordination number around palladium is 4, which is covered. For introducing this moiety, one L has to go out. So one L will go out, and it will form palladium. Bromine is here, Ar, and NH, CH2, R1. Now in this step, because you need to remove your PR, so you need to introduce a base, which is your sodium tertiary hydroxide. It takes out Br as NaBr. Also, it takes out H from your system. This H also needs to go out so that it can coordinate with your AR group. Already it is coming as a coordinating group only where group is attaching. If you want to make a proper sigma bond, it needs to clear its valency. So tertiary butanol will come out and ultimately it would form L. Since now again Br is going down, so it has to complete the coordination. Again, whatever the L has gone out, it comes into picture. This is L2, palladium. It will form NCH2, R1, R2, and there is Ar. So here this is a sigma bond, so it consider it very properly. Now at this step, because for reductive elimination, it needs to have a bond. It can't be just a lone pair which is attacking over here. So this has to be a sigma bond, and at last it would give your Ar and NCH2 R1 R2 group as your final product. NCH2 R1 and R. This is basically N is coordinated with AR, it is coordinated with CH2R1, and it is coordinated with R. This is your product which we wanted to have, and this is basically your CN coupling. We started with AR-BR, now we end up having a ARN. So this is your CN coupling, which is your emanation of arrays. This is clear. If there is any doubt, please answer the question.
Yes, ma'am. Clear with it, ma'am.
So moving ahead, what are the steps that we have seen here? So we can just write my name there. The first step that happens in this mechanism is the oxidative addition of the aryl bromide. So oxidative addition. The second, as I mentioned, that it was just coordinating with the lone pair of it. So we can consider if it is coordinating, then it is here. If it is just coordinating, it would be still there. Once it is inserting, then we can expect H is going out and then it is formed with the bond. So first, the coordination of amine is happening. Coordination of amine to the palladium is happening, which is followed by the deprotonation of amine within and making it as an amido. When amido is there, meaning it is N minus. Earlier with amine, it is N with coming as a lone pair. When that happens, and this happens in presence of base, that's why we infused a base, which is sodium peroxide, tertiary peroxide, followed by we have a reductive elimination of arylamine, where we saw AR and bond formation. There could be side product formation as well, if at all your amine is having, it undergoes beta hydride elimination. So beta hydride elimination that would give imine and ARH. So if at all that is not stable product, it can undergo, if there is any proton which is a beta hydride is available, it would try to make an amine and give the hydride to the proton to be arrived. So it can also happen. So for that matter, you need to be very careful with the reagents that you're taking and what kind of reaction you want to have. So there are certain scope of this reaction. So firstly, it is having a good functional group tolerance. Meaning, even if you have too many functional group onto your aryl site, it is not to get affected, not going to get affected in presence of these reagents. So it is having good functional group tolerance. So preferably, if you have electron-rich amines with more electron density and electron-poor arenes. So your aryl group should be poor. That means if you have electron withdrawing groups onto your array and electron rich groups like methyl, OCH3 onto your amines, that will enhance the electron density. If they are being used, the reactivity is even more higher. If you are using a primary amines, then much chelating ligand is required for the palladium catalyst to make a stabilized product. Also, we have seen a tension in the configuration. The tension of configuration has been observed at the C alpha position for intermolecular coupling of hyalurones when catalyst is using. So the meeting will be ending in next 10 minutes. Please will join the same link. The catalyst has binary some chiral ligands it is having. So this is basically if you only remember the structure, I believe something like this way. I nothing is there, but this is a chiral sentence that I believe so. So when you're using a chiral ligand, you end up having a chiral product, and when the coupling of chiral ligands are happening, generally we end up getting a retention in the configuration for which whatever side of your leaving group is there, at the same side you're going to get your product formation. It is not going to invert the configuration. So this is what is the beauty of this particular reaction. Even for the intramolecular also, when the catalyst is having over-dented ligands, if some intramolecular reaction is happening. So in that case, if your catalyst is having over-dented ligand, in case of intramolecular, it means within the same substrate, if it is going to get a reaction, so the catalyst needs to have a monodentate ligand coordinating with one end only. That would give you a retention of configuration. So we can have a sample of intramolecular coupling. Where it is also sample. This is H. This is NHAC. So this is your CBR bond and this is your NH. This needs to be coupled. That means the center, this one, and this one center. These two centers need to couple. That can happen in presence of they are taking palladium acetate, and this is organometallic. I was mentioning cesium, CO3, carbonate, Celsius in presence of toluene. So orthotoluene, if you are having binding with this side, going to bind with palladium and similarly anti-orthogonal. So it is basically it will define your position of methyl group, right? At what position, if it is ortho, that means this one. If it is para, then the CH3 would get the value position with respect to that one. And here, as you mentioned, it is a monodentate ligand, and now we are having an intramolecular thing. It is going to retain all the configuration. So what we expect to have it? We know that DR is going to go up. The H is going to be taken by the cesium carbonate, which is a place over here, and you will end up having a product like this one, where this bond is going to be formed by the bond between C and N. So the bond is going to happen between these two, N and C. AC is there already, and close the ring, and here we are having the group COO. So this is having a 93% yield. Also, there's a mentioning access of 99%. So this is an intermolecular coupling where the retention of the configuration is happening when you're taking the palladium base ligand and a glucodentate ligand, which is the para orthotoluene phosphine at 100 degrees Celsius. Now let's see the example for just a second. Intermolecular thing. Now I'm taking this is my pyridine and a substitute with pyridine, bromine would be there. This can be at any position, and I'm treating it with H and R attached. So this is my again an aryl bromide group, and this is my substrate where the nitrogen is happening. Now in this case we have palladium acetate, and there is a binap which is your parallel ligand in presence of sodium tertiary oxide 70 degrees Celsius and in common medium. This is your base, this is your parallel ligand, this is your catalyst. Now what we expected to have, wherever the bromine is would be there at any position, at that position you end up having an R damage. So this is the where the retention of the configuration is going to happen in intermolecular reactions. If there is any doubt, please let me know.
No, ma'am.
Example, some other example that we can consider. You have orthobromopyridine and two molecules are taken, and you have orthomethylpyridine. Now this is your amine substituent and this is your aryl substituent. In presence of palladium acetate, the phosphine phase system, parallel ligand, sodium tertiary oxide, 70 degrees, and toluene. So what do you think? What would be your expected product when you try?
There will be a removal of HBr.
Yeah, that is there. So your BR would go from this position and H would go from this position, right?
-2.
Yeah.
Yes, ma'am.
So one we can expect like okay, if this is happening at this position, my N and one H is still there. This is going to so this is what we are expected to have our as a product, and this has been given by which was 1996. Still,
Ma'am, since there are 2 moles of the first reactant,
yeah.
it can again react with that H and one more HBr will be removed. So another
There
thing
is
can
a
be formed.
possibility, yeah, there is a possibility that we can have one more hydrogen loss and pyridine over there. But at this moment, I don't know whether because of the steric index of pyridine, whether that product is possible or not. So at this, like major product is there. And at the moment, even if we expect, okay, then we have nitrogen here, and now this becomes a substrate of nitrogen, and when we are treating it with Br, so it should form as pyridine, moiety, like this. But so far,